Hi everyone, I am Ayman from A to Z Physics. In the previous video, we explained the interference of light. In this video, we will complete the lesson by solving a set of exercises. But first, don't forget to subscribe to the channel and to activate the bell button to watch every new video. This starts with the application number 6. Application number 6 studies what happens when we move the source vertically. We displace S by a distance y in a direction parallel to the slit to the side of S1 as we see in the picture. First question, show that the new optical path difference at M is delta prime equal AY over small d plus AX over large D. The optical path difference is equal to S prime S2 minus S prime S1 plus S2M minus S1M. So S prime S2 minus S prime S1 plus S2M minus S1M equal to AY over D plus AX over D, since S prime S2 minus S prime S1 equal to AY over small d, and S2M minus S1M equal to AX over D. Second part, the central bright fringe is not at O anymore justified. So when we displace the source, the central bright fringe will no longer be at O. Why? We have to know that the central bright fringe, the optical path difference of the central bright fringe, should be equal to 0 always. At O, X equals 0. So delta prime equal AY over D, since delta prime equal AY over D plus AX over D. When you substitute X equals 0, you will have delta prime equal AY over D. And Y different from 0, so the central bright fringe is not at O. Part 3. Determine the direction of the displacement of the central bright fringe. Assume that the central bright fringe is at a point O prime different from O. Delta of the central bright fringe equal to S prime S2 minus S prime S1 plus S2 O prime minus S1 O prime. So 0 equal S prime S2 minus S prime S1 plus S2 O prime minus S1 O prime. Why we put 0? Because the delta of the central bright fringe always equal to 0. We have S prime S2 greater than S prime S1 since the source is displaced upward. So S prime S2 minus S prime S1 will be greater than 0, implies S2 O prime minus S1 O prime less than 0. So S2 O prime less than S1 O prime, so O prime is below O. Part 4. Determine the expression of the new position of the center of the central bright fringe. The optical path difference of the new central bright fringe is equal to 0, implies AY over small d plus AX over D equal to 0, implies AX over D equal minus AY over small d, implies X of the new central bright fringe equal to minus Y large D over small d less than 0. So the central bright fringe is below O. It is displaced in the opposite direction of the displacement of the source. Part 5. Determine the expression of the new position of the center of kth bright fringe and kth dark fringe. Show that the whole interference pattern make the same displacement. So we need to determine the expression of the position of the bright fringe, X of kth bright fringe and X of kth dark fringe. We have delta prime equal AX over D plus AY over D. For bright fringe, delta prime always equal to K lambda. So AX over large D plus AY over small d equal K lambda. By calculation, we will have X of the kth bright fringe equal K lambda large D over A minus Y large D over small d. In the case of dark fringe, the optical path difference always equal to 2K plus 1 times lambda over 2. By replacing it we will obtain ax over large D plus ay over small d equal to 2k plus 1 lambda over 2. By calculation, we will finally obtain the x of the kth dark fringe equal to 2k plus 1 lambda times large D over 2a minus y times large D over small d. So we can deduce that the central bright fringe, the bright fringe and the dark fringes are displaced with the same distance, which is equal to minus y d capital over d small. Part 6 shows that the interfringe distance remains the same. The interfringe distance I is equal to x of k plus 1 minus x of k. For a bright fringe first, I equal x of k plus 1 minus x of k. We substitute the value of x of k plus 1, which is equal to k plus 1 lambda d over a minus yd over d, minus x of k, which is equal to k lambda d over a plus yd over d. Okay, implies I equal lambda d over a into k plus 1 minus k equal to lambda d over a, so I remains the same. Same calculation for dark fringe, we substitute x of k plus 1 minus x of k. Here is x of k plus 1 and here is minus x of k. We will finally obtain I equal lambda d over a. Part 7, we notice that the center of the central bright fringe coincides with the position that was occupied by the center of the 10th bright fringe on the negative side of O before displacement of S. Given d equal 40 centimeter, okay, a equal 0.5 millimeter, d equal 2 meters, and lambda equal 500 nanometers. Show that y equal 0.4 centimeter. The expression of x of kth bright fringe before we displace the source equal to k lambda d over a. 10th bright fringe below O, so k equal minus 10. When we substitute k equal minus 10, we obtain x of the kth bright fringe equal to minus 10 lambda d over a. Now, since x of the new central bright fringe is equal to the x of the kth bright fringe before displacing the source, we replace the values. We will obtain minus y large d over small d equal minus 10 lambda d over a, implies y equal 10 lambda small d over a. We replace the values and we will obtain that y equals 0.4 centimeter. Now, application 7, introduction of a transparent parallel plate. A transparent glass sheet of thickness E equal 5 micrometer and of index of refraction n is introduced just behind the slit of S1. C is the speed of light in vacuum and practically in air, and V is the speed of light in the glass sheet. Part 1. Light crosses the glass sheet of thickness E during a time tau. Give the expression of tau in terms of E and V. V equal distance over time. The distance here is E, so equal E over time, which is tau, so tau equal E over V. Knowing that d is the distance covered by the light in air during the time interval tau, determine the expression of d in terms of n and e. The speed of light in the air or in vacuum is c, so c equal d over tau, d equal c times tau, and the expression of tau is obtained in part 1, tau equal E over V. Finally, we will obtain that D equal C over V times E, and C over V is equal to N, the index of refraction, so D equal NE. Deduce the expression of the increase in the optical path difference due to the passage of light in the piece of glass. The optical path is the distance that would be covered by light in air. Before introducing the sheet of thickness E, the optical path of this thickness is E. While when we introduce the sheet, the optical path of this thickness is D equal NE. So the increase of the optical path is simply the difference between these two answers. So NE minus E equal to E into N minus 1. So S1m prime equal S1m, which is the original path, plus e into n minus 1, which is the increase in the optical path difference. 4. Show that the new optical path difference at m is delta prime equal ax over d minus e into n minus 1. Delta prime equal ss2 minus ss1 plus s2m minus s1 m prime equal ss2 minus ss1 plus s2m minus s1 m prime, which is equal to s1m plus e into n minus 1. So it is equal to s2m minus s1m minus e into n minus 1 equal to ax over d minus e into n minus 1. 5. The central bright fringe is not at O anymore. Justify. We have to know that the central bright fringe, its delta always should be equal to 0. So at O, x equals 0 implies delta prime equal minus e into n minus 1. When we put x equals 0, delta prime will be equal to minus e into n minus 1, and this is different from 0, so the central bright fringe is not at O. 6. Determine the new position of the central bright fringe and deduce its direction of displacement, if it is displaced upward or downward. The optical path difference of the new central bright fringe is 0, so ax over d minus e into n minus 1 equal to 0 implies ax over d equal e into n minus 1, so the position of the central bright fringe equal to e into n minus 1 d over a. Since n greater than 1, x will be greater than 0, and we can deduce that the central bright fringe is displaced above O. As a conclusion, it is displaced to the side where the plate is introduced. Part 7. Determine the new position of the center of the kth bright fringe and kth dark fringe and show that the whole interference pattern make the same displacement. We have the optical path difference delta prime equal ax over d minus e into n minus 1. As we know, for the bright fringe, delta prime equal to k lambda, so ax over d minus e into n minus 1 equal to k lambda, and finally we will get x of the kth bright fringe equal k lambda d over a plus e into n minus 1 d over a. For the dark fringe, delta prime equal 2k plus 1 lambda over 2 also equal to ax over d minus e into n minus 1, and finally we will have the expression of the kth dark fringe after introducing the plate equal 2k plus 1 lambda d over 2a plus e into n minus 1 d over a. We can deduce that the central bright fringe, the bright fringes, and all the dark fringes are displaced by the same distance e into n minus 1 d over a, so the whole interference pattern make the same displacement. Part 8. Show that the interfringe distance I remains the same. I equal to x of k plus 1 minus x of k. The new position of the x of k is k lambda d over a plus e into n minus 1 d over a. So x of k plus 1 equal k plus 1 lambda d over a plus e into n minus 1 d over a minus x of k, which is equal to k lambda d over a plus e into n minus 1 d over a, implies I equal lambda d over a k plus 1 minus k, implies I equal lambda d over a, same, or I remains the same. Same method for the dark fringe, we will obtain also I equal to lambda d over a. Part 9. We notice that the center of the central bright fringe coincides with the position that was occupied by the center of the fourth dark fringe in the absence of the sheet. Determine the value of n, knowing that a equals 0.1 mm, d equal 1 meter, and lambda equals 768 nanometers. X of kth dark fringe before introducing the plate was equal to 2k plus 1 lambda d over 2a. Since we have fourth dark fringe, so k equal 3, implies k of the fourth dark fringe equals 7 lambda d over 2a. The position or the new position of the new central bright fringe is equal to the position that was occupied by the fourth dark fringe, so x equal x implies e into n minus 1 d over a equals 7 lambda d over 2a, so e n minus 1 equals 7 lambda over 2. Finally, we will have n equal 1.5376. Note, if the sheet is inserted behind or in front of S1, the interference pattern is displaced to the side of S1. While if the sheet is inserted behind or in front of S2, the interference pattern is displaced to the side of S2. Application 8. White light and interference in water. Consider Young's double-slit apparatus that is represented in the adjacent figure. S1 and S2 are separated by a distance a equal 1 mm. The planes P and E are at a distance d equal 2 meter. I is the midpoint of S1, S2, and O is the orthogonal projection of I on E. On the perpendicular to IO at point O and parallel to S1, S2, a point M is defined by its abscissa OM equal A. The optical path difference delta at M, OM equal X, located in the interference region on the screen of observation is delta equal SS2M minus SS1M equal AX over D, since SS1 is equal to SS2. A. The source S emits white light which contains all the visible radiations of wavelengths lambda in vacuum or in air. Part 1. Does a red light emitted by S1 interferes with a violet light emitted by S2 and Y? Simply the answer is no, since yellow and red lights have different frequencies, so they are not synchronous. Part 2. The color of the center of the central bright fringe is white. Justify. Each monochromatic radiation of the white light undergoes interference and gives at O a central bright fringe that corresponds to its color. All the monochromatic radiations of the white light superpose at O to give again a white central bright fringe. Part 3. Compare the positions of the centers of the first bright fringes corresponding to the red and the violet colors on the same side of A. The position of any bright fringe is equal to x equal to k lambda d over A. For the first bright fringe k equal 1, so x1 equal lambda d over A. Since lambda red greater than lambda violet, so x red greater than x violet, so x of the position of the first bright fringe for the red color is greater than the position of the first bright fringe for the violet color. Part 4. The point M has an abscissa x equal 4 mm. 4.1 show that the wavelengths of the radiations that reach M in phase, so bright fringe, are given by lambda in nanometer equal to 1000 over k, and k being a non-zero positive integer. So for a bright fringe, the position of any bright fringe is equal to k lambda d over a. We substitute the value of x, the value of d, and the value of a. We will have lambda equal 4 times 10 to the power minus 3 times 1 times 10 to the power minus 3 over 2k, which is equal to 2 times 10 to the power minus 6 over k in meters. In nanometer, the answer will be 2 times 10 power minus 6 times 10 to the power 9 over k, so it will be equal to 2000 over k. 4.2. Determine the wavelengths of these radiation. Note the wavelengths of the visible light or of the white light between 400 nanometer and 800 nanometer. So 2000 over k is greater than or equal 400 and less than or equal 800. After a simple calculation, you will obtain that K is between 2.5 and 5. So K will be equal to 3, 4, and 5 after replacing the values of K in the expression of lambda. You will have lambda 1 equal 667 nanometer, lambda 2 equal 500 nanometer, and lambda 3 equal 400 nanometer. 4.3. Determine the wavelengths of the missing radiation at M. What do you mean by missing radiation? Of course, the dark fringes. So missing radiations corresponds to the dark fringes. The position of any dark fringe is equal to 2k plus 1 lambda d over 2a. We substitute the values of x and lambda, d and a, and we will have lambda is equal to 4000 over 2k plus 1. Also, lambda is between 400 nanometer and 800 nanometer. After a simple calculation, we will have k between 2 and 4.5, so k equal 2, 3, and 4. Of course, we take the value 2 since k here is greater than or equal to 2. Okay? Substituting k in the expression of lambda, we will have lambda 1 equal 800 nanometer, lambda 2 equal 571.42 nanometer, and lambda 3 equal 444.44 nanometer. Part B. The source S emits two radiations of wavelength lambda 1 equal 450 nanometer and lambda 2 of unknown value. Note here the source S is now not a monochromatic radiation. It is a polychromatic source but not a white light. We notice that the 8th dark fringe of the radiation lambda 1 coincides with the 5th dark fringe of radiation lambda 2. Calculate lambda 2. The abscissa of the center of the kth dark fringe is equal to 2k plus 1 lambda d over 2a. For the first radiation, x1 equal 2k1 plus 1 lambda 1 d over 2a. And for the 8th dark fringe, k1 must be equal to 7, so x1 equal 15 lambda 1 d over 2a. Same procedure for the 5th dark fringe of radiation lambda 2. We will have x2 equal 9 lambda 2 d over 2a. Since the two dark fringes coincide, so x1 equal x2 implies 15 lambda 1 d over 2a, which is x1 equal to 9 lambda 2 d over 2a, which is x2. And finally, we will have lambda 2 equal 750 nanometer. C. The radiation used now has a wavelength lambda equal 520 nanometer in air. The preceding apparatus is immersed completely in water whose index of refraction is n. The distance between the planes E and P is d, and the distance between the slits is a. 1. Define the interfringe distance I and calculate its value in air. The interfringe distance I is the distance between the centers of two consecutive fringes of same nature. I equal lambda d over a. It will be equal to 1.04 times 10 power minus 3 meter. The wavelength lambda of a luminous radiation in air becomes lambda prime in water, medium of index of refraction n. Determine a relation between lambda prime and n. In air, C equal lambda times frequency. In water, the speed of light becomes v equal lambda prime, the new wavelength, times same frequency. Dividing 1 over 2, we obtain C over V equal lambda times frequency over lambda prime times frequency, and since n equals C over V, we will obtain n equal lambda over lambda prime. Part C3, the interference fringes in water seem closer than in air. Why? Since I prime equal I over n, where I is the interference distance in air and I prime is the interference distance in water, and n greater than 1, so I prime is less than I. So the interference fringes in water seem closer than in air. Why I prime equal I over n? Since lambda prime equal lambda over n. Part C4. In water, 5 interference distances extend over a distance of 3.9 mm. Determine the value of n. 5 interference distance corresponds to the 5i. So 5i equal 3.9. So I equal 3.9 over 5 equals 0.78 times 10 power minus 3 meter. I prime equal I over n. So n equal I over I prime. So n equal 4 over 3. Now try to solve exercises 15, 16, page 254 on the official book. You can pause the video and start solving the exercises. You can also try to solve some of the official sessions. Thank you for watching our videos. Please don't forget to subscribe and press the bell icon for latest updates.